So we left off last time with talking about double slit, right? So we had two coherent light sources, and we saw that they created an interference pattern, right? So we left off with that, and what I didn't get a chance to finish was talking about interference patterns and with intensity. Right, so we know. So let's take two electric waves. We have, let's say, E1. Can everyone see this in the back? No? E1 is equals to E cosine of omega t plus phi, and this is my phase shift of something. And then my second electromagnetic wave is simply E cosine of omega t. So I have plane waves traveling, and they're both polarized in the same direction here, and they're both sinusoidal or cosinusoidal in this case. And so at each point they're traveling, they have a certain intensity, which is given by the pointing vector, which comes out to 1/2 epsilon naught speed of light e squared at some point p. So these two are traveling, and pick some point p where they're traveling through, and that'll be the given intensity for the respective waves. And we know that the intensity is proportional to the electric field squared. So at point P, we will have a superposition of both of these. Right? So each of these may have the individual E squared, but at that point P, the intensity overall has to be a superposition of both. So the superposition principle, we can't really escape it. Right? It comes back to us. So to find the intensity at point P, we know that it's proportional to E squared. So the electric field at point P squared, this is going to be equal to E1 squared, well, E squared plus E2 E squared over there, minus 2 E squared cosine of pi minus phi. This equals 2 E squared plus 2 E squared cosine of phi. Right? I'm pulling the this identity when I take pi of cosine. I can basically ignore that part. Well, not ignore, but if I shift either sine or cosine by pi, right? So if I have my plot, let's say I have cosine, something like this. This is my pi over here. This is 2 pi. So if I shift the whole thing by pi, this thing will basically flip, right? So if I shift this by pi, I'll get something like this. So whatever I have the positive there, I would normally should get the negative there. So basically, I can take the pi out and then flip the sign, and we're good there. So I can use the half angle identity here, which is 1 plus cosine of phi equals 2 cosine squared of phi over 2. When I use that there, I get EP squared equals 2 E squared times 1 plus cosine of phi. This equals to 4 E squared cosine squared of phi over 2. Right? So I combine those two E squares. I factored out the E squared from there. So I get this boils down to that. And then I apply my half angle identity, and I get that. And from here, I can take the square root of it because I'm looking at EP squared. So therefore, from that, the electric field at point P is going to be 2E absolute value cosine of phi over 2. Right? And this is the amplitude in a two-source interference. So that's the total amplitude at some point. I have two separate sources with two separate electric fields, or at least same amplitude but just different phases. They come in at different times, and that's the overall intensity of that. So intensity we know is the time average of pointing vector. Again, remember, pointing vector by itself we can't really do too much with because it's because of the the way the units are set up. So we take a time average so we can average over a long period, and then we get an actual answer. Otherwise, if you have cosine terms, sine terms in there, at some point you'll have a maximum, at some point you'll have a minimum. It doesn't give you, I mean, at some specific point in time you can have an answer, but if you're looking at overall actual intensities and stuff, it doesn't make sense. So remember, time average is always important for the pointing vector or for the intensities. So this is going to come out to whatever the electric field is at that point squared over 2 mu naught c. So this is going to give me 1/2 square root of epsilon naught over mu naught EP squared. And this is equals to 1/2 epsilon naught c EP squared. And I plug in that EP squared over there. So therefore, this is going to come out to 2 epsilon naught speed of light e squared cosine squared of phi over 2. So we can see that the maximum intensity happens when they're both in plane. There's no phase shift here. So you'll get a maximum when phi is 0. Right? So when phi is 0, you get I, or intensity, let's say, is I equals to I naught, which equals to 2 epsilon naught c e squared. Because cosine of 0 will give you 1. So to get the maximum intensity, those two have to be in phase. And that makes sense. If they're out of phase, then they may interfere destructively, and obviously the intensities won't be as high. So this makes sense that they both have to be in phase. I think that's about it. So now we can look at thin films real quick for a couple minutes. So I'm not going to dwell too much into it because it's just a repeat of Snell's law with some minor adjustments to be made. So if I have some media here and I have some film on top with some index of n, some thin film, and this is some thickness t. So you can either have constructive interference or you can have destructive interference based on the phase. So the constructive interference between the two is two reflective waves occurs different place for different wavelengths, obviously. So you can see more of like a rainbow effect. If you ever saw oil on water or something, you can see like a rainbowish hue on there, right? And that's because of this. So basically what happens is you have some ray coming in, some of it will get reflected off here, some of it will go in, and then we'll get, it has some index of refraction obviously, so it will refract and it will reflect back out. And then you see this over here as, at some point P, as basically two separate wavelengths coming in, and that's how the whole thing essentially works. Now for this, you have the formula is 2t equals m lambda, m being the equivalent to n here, so m is 0, 1, 2. So m is going to be 0 plus or minus 1 plus or minus 2, and so on. And this is going to give me constructive. Right? And then for this, you'll have no phase shift here. For the destructive, you'll have 2t equals m plus 1/2 lambda, and this will give you destructive. And then it also depends if this is just something that reflects but nothing else goes in. Depends on if this also has an index. Right, this will have, let's say, some index n2, this is some index n1. Also this index over here will have something, let's say this is n3. So based on, you have some thin film here, so based on what, let's say, the relationship between n1 and n2. If n1 is larger than n2, then you'll have one type of relationship. If n2 is larger than n1, you'll have the opposing relationship between constructive and destructive. So this actually is detailed quite well in your book, and just glance over that real quick, and you guys should be good. So that effectively takes care of coherent light sources that we'll be looking at. So, but today, what I wanted to spend most of the time on, or all the time, rest of the time on, is expanding on simply when yes. M? Oh, you mean N or M? Sorry. This M, right? Depends on what I'm asking. If I'm asking you the 0th order or something, then you can say that basically that's, if I'm looking at it from, let me see. If I'm looking at, remember yesterday we looked at, or yesterday on Monday we looked at the separate intensities and all that lights form, and we saw that at certain angles you have certain maximas and so on. So if I draw the line through the middle, it stands to reason that I should have a maximum, right? So this is my 0th order for the maximum, where M is 0, and then M1 on plus or minus, and then M2 plus or minus, and so on. And same thing with the destructive. With the destructive, even if you have a 0 here, you'll get some phase shift there. So it'll be on either one of the sides. Plus or minus will be in through the middle between the maximas. So it depends on what I ask. If I tell you, the 4th minima or something, then you say, okay, M is going to be 3 at that point, because the first one obviously is 0. Second one is M equals 1. Third one is M equals 2. And the fourth one is M equals 3. So it depends on what you're being asked there. So if I ask you to find the 5th maximum, then you use the first one, and your M there will be 4. If I ask you to find the first maximum or first minimum, then M will be 0 there. So, makes sense? All right. Any other questions on this? No? You guys already experts? Or just haven't done the homework yet? So who went home and tried the grape thing for themselves? Come on, we're living in a first world country here. Not having a microwave is a third world problem. So if you guys do go home and try it with grapes, I suggest you guys put some sort of a glass cup or something on top. I brought the glass cup with me, but it was too big for the small microwave. So just check it out what happens when you put glass on top and conduct the grape experiment. It's quite spectacular. That's why I make sure it's glass and not plastic or something that can melt. So, and don't leave it for too long. If you smell like something like glass burning or something, just stop it and get it out. Again, it's just a suggestion, not a requirement, so I'm not going to be held liable for any damages. All right. So, like I said a couple minutes ago, we looked at 2 light sources, right? 2 coherent light sources on Monday. Now let's expand on that and look at multiple light sources. So if I have n number of light sources, right? I have source here, 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 or it goes on. So like basically think of it as slits there, and there are n of them. And I have plane waves or light coming in. And let's say the distance between each of these is a distance d. Right? So once the light comes in here, let's say it gets to this point, each one of these openings is going to act as a Huygens source, right? Which means that I have multiple n number of light sources going out. And what's going to happen here again, that once these come in, you'll have spherical waves being produced, and they go out, and each one of those Huygens sources, they'll interfere with each other, and you'll get some patterns. So the question we can ask ourselves is the same one we asked before. What will happen if you look at some distance far away? So I'm over here. I look at it at some distance L. I want to know what the interference pattern is going to be. So let's say I put a screen up there. I want to know what the pattern is going to look like. And I may even generalize it to say, okay, this is some distance x. I can ask you to find the distances between each of those maximas or each of those minimas. So I can come up with a linear description for the distance there. So again, like before, we'll take some angle to be theta. Remember, we're working with hyperbolus here, so the theta is really an approximation. It's a better approximation if you're farther out. So that's something to keep in mind. So what you'll have is you'll have constructive interference exactly the same as you did before with the two light sources. So constructive interference you'll have at sine theta n equals n lambda over d. Right? That doesn't change. And if you're dealing with small angles, so basically when the distance is really large, we can make that approximation for sine. So I mentioned this last time, sine of theta for small angles is simply theta. And of course, we're working in radians over here. So what this will essentially become once I take the small angle approximation is I'll get theta n equals n lambda over d. So if I want to express this in terms of a displacement from 0, if I call this point 0, I can do the same. I can say x of n is going to be L n lambda over d. And this is my displacement. And you usually express this in either meters or centimeters or whatever the right units call for, but usually meters or centimeters. And at this point, you may say, big deal, it's the same exact solution that we got from the double slit interferometer that we looked at last time. Yes, same equation, no different, but the d here is, again, just the separation between the sources and not the distance between the slits. So it's obvious that it's the same because if these two are interfering constructively, so let's say this, they're all interfering constructively, then you'll also have at some point destructive interference. It's not surprising that we get the same result for the constructive interference because they're all some distance d apart, and they have to interfere constructively at some point. But the big surprise here comes when we talk about the destructive interference when I have multiple light sources. So to derive this properly is actually quite tricky and math intensive, and it's beyond the scope of this class. And some of you that are moving on in physics, taking higher level classes, I'm sure at some point you'll see the derivation for this. But until then, if you don't want to wait, you obviously can look it up on Wikipedia or something. But what's different about destructive interference, and something that's not so intuitive, is that if I have something like n sources, and basically I have n sources, that therefore I'll have n amount of maximas. Now I'll have, instead of having n amount of minimas, I'll have capital N minus 1 amount of minimas. And by minima, of course, I mean complete destructive interference. What's that? Big N minus 1. Big N being the number of sources I have. So, and again, I have to say this is different from the small n. So if you remember, last time we looked at the case when n equals 2. We had two sources. Therefore, last time So last time we looked at the case when we were looking at big N was equal to 2, right? We had 2 coherent, distinct light sources. Yes. So the big N is just simply the number of light sources you have. Right? So it can be, it's basically a given amount, set amount. Not necessarily a set amount, but basically that doesn't change. And if you want to think about it in terms of 218 terms, they're like nodes or antinodes. Right? So you have at certain points you have maxima, certain points you have minimas, or you can think of them as different orders. They don't necessarily correspond to how many light sources you have. So even if I have one light source and some sort of a slit, or 2 light sources, I can have infinite amount of little n's, right? I can go out as far as I need to, right? But the big N is just simply the number of light sources I have, and that is completely independent from the number of I mean, it's not completely independent, but it's independent of what I'm looking at in terms of small n. Does it make sense? Yes. Yeah. So if I say, if in a question, like if I give you a question like this, I'll say you have n light sources, find the diffraction, find the third constructive interference, and find the fourth destructive, or something like that. So you can call upon the formulas and then calculate those. So, all right. So yeah, I had n sources there, and therefore, if we're looking at the minimas, it's 2 minus 1. This is equals to 1, and so we have one minima between the maxima and the minima last time, right? But that's not the case anymore for when we have n is greater than 2. So if you look at the intensities for this, so the intensity again is going to be in watts per meter squared, right? It's energy per time or an area. So if I take some, I'll have some minimas. Oh, sorry, I'll have some maximas over there, there, and this is a function of theta, angle, right? And again, we're working in radians. So this is where, let's say my theta is 0. Right? At 0, I have a maxima that's given, that's not really negotiable. Everyone knows that. So at angle theta is 0, I have a maxima. So if I have some light source straight ahead along that plane, I'll have a maximum. And at some point here, let's call this theta 1, and that's when I calculate that over there, I'll have n here is 1, so I'll get lambda over d. I'll have another maximum. Let's call that angle theta 1. Let's call this angle over here theta 2, and this is going to be 2 lambda over d, and that's my third maximum. So this is where the n's come into play. Let me erase this a little bit. Can everyone see that? So this is my first maximum, second maximum basically when my n is 1, third maximum when my n is 2. Now, the number of minimums here between these two is not simply 1 like it was before. So the number of minimas between these two light sources is going to be n minus 1. And to better demonstrate that, so the minimas I'll get are going to be something like this. Right? Those are my minimas there. Those are my minimas there, and they go on. So I'll have n minus 1 minimas here, n minus 1 minimas over between theta 1 and theta 2. So it's not simply I have one minima between theta 1 and between the maximas like I did with 2 coherent light sources. Right? Now I have n minus 1. So if I have n, capital N, light sources, then I'll have uppercase n minus 1 number of minimas between each of the maximas. So that's where they fundamentally differ. So if I pick something like this over here, between I have my maxima here and I have my first minima starting over there. So if I look at this angle here, and I call that delta theta, change in my theta. So I want to measure the width of this line basically. So I have my maxima over here, and the minima starts over there. So I'm looking at the width of this particular maximum peak, right? So this angle, our delta angle, is going to be lambda d over capital N, and so I have to take my word for that. So, but we know that d over n right here is theta 1, right? This is theta 1, so my delta theta is going to be theta 1 over n. Now if n is so basically my peak width is n times smaller, right? So if my n goes up, then my width will get narrow. Does it make sense? So, and if n is extremely large, then the peaks become extremely small. And again, there's another major difference between the single slit and the multiple slit diffractions. So each one of these slits can count as a light source, therefore you have n number of diffraction. So the larger the n is, the higher those peaks will also be. I mean, they have to be there. And you may, as I mentioned, we looked at intensity as a proportional to E squared, right? Intensity is also proportional to n squared. And you may ask, why is it not linearly proportional to n? If I have n number of light sources, then I expect my intensity to be n times as much. So you may be thinking that I'm violating some sort of conservation of energy here, but it's actually easy to see that it's not the case. So suppose I increase n by a factor of 3, right? What's going to happen then? My electric field vector is going to be 3 times larger, which means that my pointing vector is going to be 9 times larger. So I'll get 9 times more light. So, but you may say, wait, now that's a violation again of conservation of energy. 3 times more sources has to be 3 times more light. How can it be 9 times more light? Well, what you overlooked is that if I make n 3 times larger, then the width will be 3 times smaller, right? But then it'll get narrower by a factor of 3. So it'll get narrower by a factor of 3, but higher by a factor of 9. So if it's higher by a factor of 9 but narrower by a factor of 3, then my overall increase in my light intensity is of just a factor of 3. So this makes sense. You get a factor of 3 larger or more intense light for 3 times the number of light sources. And again, so this means that there's no violation of the conservation of energy. If there's ever, if you guys notice some conservation of energy being violated in physics, then there's some hocus pocus going on, because that's not basically conservation of energy is the cardinal rule of physics, and that's basically what everything is based on. All right, so let's look at laser with some grading. So if I look at a laser and I have 2,500 gratings, which means that I have 2,500 lines per inch here, and my distance I'm looking at between each of these is d equals 10.16 micrometers. The wavelength of light I'm looking at, the red laser I have over there, that's going to be 6.3 times 10 to the negative 7 meters. If I'm looking at some distance 10 meters away, so L equals 10 meters away, and I want the 0th order maximum, well, which means that n equals 0. First order will be n equals 1. Second order is going to be n equals 2. Different books, different people have different bookkeeping for this, I guess. A lot of people will say this is your first order, second order, third order. Some people say this is your 0th order, first order, second order. It's really different. It really comes down to well, who's dealing with it. But basically, I know your book calls this first order, second order, third order. So, I mean, I'll probably just say no at n equals 0 or n equals 1, but I'll be specific. So, but we know that for the maximum at n equals 0, my theta 0 has to be equal to 0 degrees. Right? Like I said, that's not really negotiable. You get a maximum at angle theta 0. And again, this is providing all the sources are in phase. For my n equals 1, my theta 1 is going to be 3.55 degrees. N equals 2, my theta 2 is going to be 7.1 degrees. So that's more or less how they would play out with that red laser if I have a diffraction pattern or diffraction grading of that 2500, and given the values of the red laser and the distance between each of those gratings. If I'm looking at some distance 10 meters away, I can expect those angles to be more or less accurate. Now, if I want to know how wide those widths are going to be, I'll have to know how many slits I'm using. So if I have 2500 slits, yeah, that's all well and good, but am I actually using all 2500 of those slits? For instance, if I have some grading thing like this, I have a bunch of lines in the middle, maybe my laser is only encompassing a small amount of that, right? So I have to look at what the width of my laser is. Let's say the width of my laser, in this case, would be 2 millimeters. And this grading here, as I said over there, is 2500 per inch. Right, so I want to know how many slits I'm using. So my laser beam, if I take it to be 2 millimeters in size, then my n here, once I do the calculations, is going to be 200. I'll have 200 of those slits. So now using that, I can calculate how wide my width or my intensities are going to be. So the width is, again, as I mentioned in the board in the middle over there, my delta theta is theta 1 over n. Theta 1 here is 3.55, so I get this equals to 3.55 degrees over 200. This is going to give me a measure that's going to be 1 arc minute. So this 1 arc minute is 60 times smaller than 1 degree. Right? It's 60 times smaller than a degree. That's what I call an arc minute. So it's a really, really narrow peak. But then again, in this regime, everything becomes relative. We can actually even deal with arc seconds. So, and we'll get to that in a minute. So that's my arc. That's my the delta theta. If I look at delta x, how wide those projections will actually be, it's going to be around 3 millimeters based on these calculations. I mean, it will be larger, but you can't really see this because the limiting factor here is going to be always going to be the divergence of my laser beam, and we'll get to that again in a bit. So I know that the divergence of my laser beam is actually about 1 arc minute. So it actually more than 1 arc minute. So if I have a resolution, if I have a diffraction of 1 arc minute, and my divergence of my beam is actually larger than that, I can't actually discern, or I can't see something 3 millimeters wide. And we'll discuss that again a bit. Now, I mentioned all that for red light, right? Red laser. So it's a distinct frequency for a distinct wavelength. So what if I have white light? What's going to happen? Well, we saw white light last time with those diffraction gratings that I handed out. So something similar will happen here. So if I take, again, intensity versus angle, and that's my intensity, watts per meter squared. and I'll get something like this. I'll get a peak, I'll get a peak, I'll get a peak, right? And I'll have a bunch of minimas in between these peaks, and of course these minimas are the number of minimas I get are going to be n minus 1, right? And if I say that this is my theta 0, this is my theta 1, which is equal to lambda over d, this is my theta 2, which is going to be my 2 lambda over d, and then you'll see so on. Now, when you do this with white light at 0th order, you'll always get white light, because I mean every frequency has a maximum at that particular angle, that particular 0. So at 0 you'll see white light, and all the colors have their max at 0. But the first, second, and even higher orders, you'll see the colors walk at their own pace, right? They won't necessarily follow the other colors. So a smaller wavelength, the smaller the wavelength is, you'll see that that's closer it is. So for instance, I have my red peak over here. This is my red, all the peaks. Red peak over here. My blue peak, if I can find my blue marker. My blue peak will be somewhere over here for this one. And same thing, for this one, it will be somewhere over there. So you'll see that the different colors, different wavelengths, their peaks will shift, and you'll get again another rainbow-like effect that you guys saw last time. So the spacings, of course, will depend on what my wavelength is. The smaller the wavelength, the smaller the distances will be, and so on. So our equation that we derived so far will only work if we're looking at something really far away, right? The equation I looked at over there. And therefore the angles of thetas that we're looking at, they're only true when you're looking at some distance really far away, at least really far away relative to the distances between the gratings. And because the surfaces that we're looking at, their maximas are hyperbolas like we looked at last time, and its angle is only an approximation if you're very far away. But however, we can do something clever if you want to look at something close by, and we can go to lenses for that. And let me look at that. So we discussed lenses briefly last Friday, right? We looked at the ray diagrams, their maximas, or not maximas, but basically the focal points and so on. So if I take a lens, converging lens, here, and I have something over here, and I have a bunch of slits over here, and I have plane waves traveling and coming over here. They'll hit one of those slits, and they'll create their own Huygens source, therefore their own discrete individual light source, and they'll go about. Now, let's say I'm looking at some light over here coming in at some angle there, and some light over here coming in at some angle over here, right? So what I'll see on this end, I'll see something like that, and then so this is going to be my first order, and over here that's going to be my 0th order. So, and this is my focal point over here, right here. Now, the important property about lenses that we didn't really discuss last time is that they preserve the angles. So when it's closer, if I'm looking at it at some angle away, it preserves the angle, allowing me to, well, I mean, still maintain that angle on the other end. So I can look at something close, quite close by. And we did that. You guys did that last time. I handed out those slides, and you guys held it close to your eye, and you guys looked at that white light. It's the exact same thing. Basically, you're bringing it close to your eye, so the distance between the grating and your eye is quite small. But because your eye itself is inherently a lens, you can preserve the angle and actually see the different peaks. So you guys, everyone here at least that showed up to lecture on Monday, you guys saw that, right? With the white light, I turned the lights down. You guys saw the shift, and so I actually jumped the gun. I didn't actually tell you what that was. It was white light, but it was diffraction grating. So it wasn't just two slits like I led you guys to believe. It was actually multiple slits. At some, I forgot what the gratings was, but you guys looked at that with the white light, and you guys were able to see a sort of like rainbowish effect at different angles. And if you guys center that and look at the middle, you can see the middle at the one point, and then if you look to the sides, you'll see rainbows, but in the middle you'll see the white light because all the maximums converge at that point. So we can look at we'll look at that again. Might as well look at it now. It can be a small break. So I have different gratings this time. So what I have here, not as many again, but pass them around. Pass them around. So that again is a diffraction grating, and so this is a white light source, and you guys should be able to see even with the lights on, but I'll turn them down for the dramatic effect. I don't have enough for the whole class, so you guys should share, so just pass it around. Right. Do you guys see it? You guys may need to find the actual orientation of the slits. They'll look good in anything. I don't know what you're talking about. Now, while I have the lights, while all those are passed out, let me talk a little bit more about it. Oh, where are my markers? Aha. Actually, I don't need to write anything. So those gratings that you guys have, you can actually even see that with the lights on top. Now, you can use these gratings to do atomic physics. So atoms and molecules which emit very distinct frequencies and therefore very distinct wavelengths, when you look at them with the grating like that you guys have with you, you can see very distinct places where the lines fall. So for example, neon, which I have a neon light, I'll turn on in a little bit. It's not a continuous spectra like you see with white light, and you see very distinct places where you see maxima. So you'll see many reds and several oranges, and then it'll go down and you'll have some green. So using the gratings, you can find out what the what wavelength is being emitted by whatever gas, atoms, and so on. And with that, you can also look at their strength. Well, also using their strength, you can enter the domain of atomic physics, basically. And that's more or less the principle of how they determine the makeup of other planets and other galaxies and so on. So they put some sort of, they have some light coming in, they put some sort of grating, and based on where the lines fall, they say, okay, this is we're getting light or discharge from hydrogen, from neon, and so on. And that's how they're able to look at that. If you guys ever get a chance to look at mercury lamp with these gratings, it's actually quite beautiful to look at. It has many colors. All right. So what I have here, I have no idea what this one is. Wait, no, I don't. This is hydrogen. This hydrogen? Yeah, this has to be hydrogen. So let's look at hydrogen, and then we'll move on to helium, and then neon. So this is my hydrogen lamp. I don't think any flies in here, so you probably shouldn't. Yes. Sort of. So you'll see one peak, and I think you'll see some peaks at different distances, right? Right. I can pass them around so everyone can get a chance to see it. Actually, let me borrow it. I haven't seen it. So you guys may see this like below the horizon. You'll see like a red, and then you'll go down to orange. You'll see green, blue, and towards the side you'll see like less intense ones. But the maximum at the middle you'll see a line. Did everyone get a chance to see? Shall I turn the other light? Has everyone seen the hydrogen one? Yes? All right, so let me turn on the helium one. Let's look at it. Yep. So these peaks will be off to the sides. So you have to move it around. So to either side you'll see purple, red, and so on. So have they made their way around? Has everyone seen the neon? Sorry, has everyone seen the helium? All right. So let me turn the neon on now. All right, do you guys see what I'm talking about when I mentioned you'll see a bunch of reds, and they'll slowly progress to orange, yellow, and then eventually you'll see a little bit of green. Does everyone see that? Has everyone been able to see it? Or should I wait a couple more minutes? Oh, up there? Yeah, 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 I see that. That's coming from the lights above. So if you turn those lights off, you should not see that spectra. Oh, maybe. Let's see. Let's turn everything off. We can have our own little raven here, right? No, it's still coming from light in the back and all that. All right. Has everyone had a chance to see? All the lights are all these on? I don't know, we can try. Is it cooler with all the lights on? Yeah, it's sort of overlap. All right. So let's take a quick 2-minute break. We'll meet back here. So far we looked at multiple gratings. So I mean, in the last lecture we looked at 2 gratings or 2 slits. Now we looked at multiple slits. Let's look at the interference pattern if we have 1 slit. So even if you only have 1 slit, there will be directions in space where you'll have where light plus light will produce darkness and light plus light will produce more light. So there'll be directions where the light interferes constructively, and there'll be points where the light interferes destructively. Now this is given another name. It's called diffraction. I mean, although it's still the same. It's interference. We call this diffraction for some reason. But I mean, if you want to look at it as the same, it actually is the same. The equations more or less are the same. The theory behind it is more or less the same. So it's still interference, but they just give it a different name. So it's exactly the same physics. So it all comes down again to Huygens principle. So if I have something like this where I have 1 slit and I have plane waves, light like before, traveling through, and if I'm looking at it at some distance far away, some angle theta, right? And then of course this will give me the linear separations. So they will be emitting light going through at the same frequency and therefore the same wavelength, and all of them will be in phase. And so you'll have some angle and some linear separation where you'll have maximas and minimas. And so basically, you can think of this like little small tiny little Huygens sources spread out all throughout. And it's actually not quite so easy to again, to derive all where the maximas and the minimas come from. It's reserved for higher level physics, but you'll see that again in higher level physics. So one thing that's obvious again here, and that's non-negotiable, is where the 0th order or the 1st order maximum lies. So my theta 0 is still going to be 0 degrees. That is non-negotiable. You'll get a maximum at that point. It's a matter of symmetry for this problem. And if the sources are in phase, then you can see that you're going to get a maximum at that point. The minimas, again, are going to be very tricky. So the minima for this falls in the following locations. The minimums you'll get at sine theta n equals n lambda over a. And by a, I mean that's the aperture of this, the width of that of the slit. And if I take a small angle approximation, this will be equal to theta n. Again, remember, small angle approximations, I'll be working in radians, so don't forget that. So your first reaction may be that I screwed up. The minimas here are where the maximas were in the previous case. And well, the situation now is different. You're only dealing with one slit. So the best way you can see that this equation is not wrong is by the following. So suppose that you take the angle theta where n equals 1, and then the reflection that you see there will tell you that if I have these 2 points here over there, those 2 are Huygens sources, and those 2 have a difference in path length, right? So between these 2, let's say I have a difference of wavelength lambda, and also have different points in the middles. So between this point here and this point here, I may have a difference of lambda over 2. And because, like I said, each individual point along there acts as a Huygens source. So at different points, I'll have different variations. So at some point, when I have the shift being lambda over 2, I'll have destructive interference. While I have the shift is lambda, I'll have constructive interference. So basically, I have the width of A, and every point along that opening, every infinitesimal point or D point, if you want to call it, they count as a Huygens source, and they interfere. So the upper half, there will always have one Huygens source that will cancel out the bottom half, right? So when I have that, I'll get, basically if I have the upper half canceling out the bottom half, then I'll get a minimum. And you can do the similar reasoning for the angles as well. So this indeed is the correct equation. So if I look at theta 1 for this is going to be lambda over a. Theta 2 is going to be 2 lambda over a. And again, these are where you'll find the minimas. And if you want to find out where they fall on the screen, it's the same thing. My x1 is going to be L lambda over a. That's where the minimum will fall. So what would this pattern look like? I mean, obviously the equations here are different. So let me plot this. So again, I'm looking at intensity versus angle theta. So I have watts per meter squared over there. So my intensities will look something like this, right? So this is my, let's say, I naught, my maximum intensity, I naught. And up to here, at this point, I know I'll get some minimum. So this is my theta 1, that's lambda L over A. At this minimum, it's going to be 2 lambda or 2L lambda over A, and so on. So over here, I have my maximum intensity. I'll call that I naught. My second order, or however you want to look at it, my intensity, this is going to be 4.5% of I naught. The next next maxima is going to be 1.6% of I naught. And right here, this pattern that you see is called the diffraction pattern. So when you look at a diffraction pattern, something like this, you'll see a very broad center for a maximum, and then from that point on, you'll see dark spots on either sides, and you'll see like very faint lights coming from, again, from and in between those. And we know from this the width of this is really x1, and is equal to L lambda over A, and that's again the equals to the width of the maximum. So this really is a measure of how wide the center maximum will be when you look at it on the screen. Now comes something completely non-intuitive as for you guys as well as for me to think about. Now, if I make A over there, my aperture length, really small, extremely narrow, then what you'll see is this peak is going to be extremely wide, right? It makes sense with this. If I make A small, then my maximum peak here will get quite wide. And if I make A large, then my peak here is going to be very narrow. So that's not very intuitive. And this can be demonstrated with the variable slit, which I don't have, but I mean, you guys can do this demonstration at home real quick. I mean, if you guys, I'm sure everyone has laser pointers. Right? So take a laser pointer, keep it on at some point, and if you take those 3x5 cards, poke a hole, and if you slowly cover the hole and you look at it, you'll see a broader peak. If you know the hole is wider, you'll see a much narrower peak, to a point where if the laser is going all the way through, then you'll just get one spot. And it's not quite so intuitive. Now we have so if instead of having that's for the circular slit, so if I look at something that's a vertical slit, so let's say now instead of that vertical slit I looked at, if I have a circular opening, I mean, you'd obviously see the same intensity pattern, more or less. You'd see something like this. But now what's going to happen is, if you want to think about it, if I look at the top of it and if I rotate this about its axis, then what I'd get here is I'd get some circle with a gigantic maximum, and I'll get little rings on the outside, and the rings of light represent the maximum. And again, the middle center here is theta being 0, and over here this is going to be theta 1 and theta 2 and so on. Now, I had a demonstration of this that I made for last year, but I couldn't find the file. If I ever find it, I'll post it on the website. So the circular geometry for this is going to be a bit different. Now, where theta 1 would fall, from that you'll say, okay, it's lambda over A for the minimums. But in this case, it's actually not true. What you'll get here is 1.2. Actually, if you want to be more precise, it's 1.22 lambda over A radians. And it's not simply just lambda over A like it is over there. And you sort of have to take my word for this, and it comes because of the circular geometry of this. And this raises in physics an issue in physics that we call angular resolution. Now, this can be quite limiting at times. So suppose that I take a pinhole and I look at 2 different light sources from 2 different directions. Now, they could be anything. They could be street lights, they could be headlights from a car, whatever the case may be. And if I look through that pinhole, each of those sources will give me a diffraction pattern. So if I look at, say, headlights of a car, so if I look at headlights from a car, I get something like the pattern we saw up there, maximum peak. I'll have my minimums, and same thing over here. Right, I get maximum, and the same thing on the outside. Now, if we make the angle between these two sources smaller until they basically start getting closer, now the question we can ask ourselves is how close can they get to a point where we can still say, yeah, those are two separate sources. Now that's what is called angular resolution. All right, so if I have, looking at two sources, they're obviously away at two separate angles. There can be some angle or some maximum or minimum angle that they can come to, at which point I can say, yeah, those two are still separate sources. Now, how we define angular resolution is both the light sources we take to be the same strength, and let's assume for now that they're also monochromatic for simplicity, sort of like our spherical cow approximation here. So they're monochromatic and they have the same intensities. And the criteria that's generally accepted is if I have my maximum here, and if I have this source here, I can bring this, let's say I have maximum here in the middle, I have the maximum here in the middle. I can bring this maximum close until I hit the point where it's somewhere over here where I have the first minimum. I can bring it in that close, and that's generally the angular resolution. And I cannot bring it any closer than that, or I'll have no, I can't bring it any closer than when I have this first complete dark spot. If I bring it any closer, you'll say it's a single source. And again, it's not exactly more or less a hard sell because everyone has different vision. So we'll actually calculate this. And what this criteria here is called, so I have my maximum, I can bring the other source's maximum up to the first full minimum I have. And this is called the Rayleigh criterion for resolution. So the separation of these two sources has to be larger than this angle of theta 1, 1.2 lambda over a. And that's what we said that the first, where the first minimum falls, right? So the separation between these two sources when I bring it in together has to be larger than this angle. And it's of course a function of a, so it's a function of the width of the pinhole you're looking at. So if a is larger, then obviously I can have a smaller angle, theta 1, so I can bring it in closer. If a is smaller, then obviously the angle will have to be larger. Again, this is something else you can demonstrate. I wouldn't recommend you do it while driving a car, but it is something you can look at as a passenger at night. Now you have headlights coming in the other way, take a 3x5 card, poke a hole, and then put it by your eye, and you can see. Well, so at some point you can have, as the light comes closer towards you, you can sort of see that you can resolve it better as opposed to it being farther away. And even without that, I mean, at some point if the car is really far away, it seems like it's really one source of light coming towards you. So that's the Rayleigh criterion for resolution. This is the absolute closest you can get. I mean, at least this angle. Otherwise, if it gets any closer, it'll just be like one light source for you. So it sort of makes sense, right? If I have my maximum coming in anymore, it'll sort of blend with this maximum, and it's going to be impossible to tell the difference. And this is again what we call the diffraction limit of angular resolution. And it doesn't matter whether you have a pinhole or whether you have a lens, be it a elliptical lens that we discussed for telescopes, or concave mirrors, whatever that you're looking at. In all cases, you'll be stuck with the idea that the best you can do in terms of angular separation is that 1.2 lambda over a. Again, this is in radians. So if we take a lens with diameter a is equal to 20 centimeters, and my wavelength that I'm looking at, let's say, is 5,000 angstroms. Again, remember, angstroms is 10 to the negative 10 meters. And if I take those two, then my theta 1, my angular separation, will have to be half an arc second. Right? If I take a much larger diameter for the telescope or for the lens, and my A is, let's say, 2.4 meters, so it's about 12 times larger, then the angle I get for this, my theta 1 here, is going to be 1 over 25 arc seconds. So this is 12 times, about 12 times better than this one. So because again, A is about 12 times larger, so I'll get a 12 times better resolution. So the larger you make your telescope, the better the angular resolution will be. So now, if I were to have a telescope, and we have a bunch of these like extremely high-end telescopes out in Chile and in the United States and so on. Now, you may think that if you have an aperture of 2.4 meters, or A is 2.4 meter diameter for the lens, then you can tell apart stars that are about 1 over 25th arc seconds apart. Right? No, that's actually not true. If I have those telescopes, you can't even tell it apart if it's half an arc second apart when you're looking at ground telescopes. And the reason for that, we briefly discussed that when we were looking at the scattering stuff, right? So air is quite turbulent. So because you have a lot of turbulence in the air, the image moves on your photographic plates on your telescopes. And astronomers call this seeing. So what happens is when you have the plate, when because of the turbulence, you'll see that the image basically smears around. And so you'll basically get a smeared image, and astronomers call this seeing. Now, the best you can do is half to approximately 1 arc second resolution from ground telescope. So how do we get around this? Well, that's why we have the Hubble. Hubble's been retired recently, which is a shame, but Hubble actually has about 2.4 millimeter diameter for its lens. Now, Hubble is out in space, so there's no air, which means that there's no air turbulence. And so its theta 1 is approximately 1 over 25th of arc second. At shorter wavelengths, the resolution can be even better. So let me show you a picture of what the Hubble took. What fell? Oh, stapler, sorry. Showing up. Is anything showing up there? God. Hold on. I just have to log in. Still can't select a source. SPC. There we go. All right, so this is a picture of a supernova called 1987A. Well, there's only to write down. So it's a supernova explosion, and it happened in February of 1987. Now, the light that this supernova right here happened 150,000 light years away. So in principle, this explosion you see here occurred about 150,000 years ago, minus or plus or minus 21 years, I guess, 25 years. But what you see here is that the difference between the center here and the edge here is about half an arc second. And you're able to discern, so you have these two light sources, and you're able to discern the difference between those at about half an arc second apart. And this is the strong A-part picture in 2007. So this was taken by the Hubble telescope, and when we saw the supernova. So that's an interesting one. So the angular resolution of the eye, our eye, is about half an arc minute, and it's impossible to get it to be any better. More or less, usually the average is about an arc minute, not half an arc minute, but it's anywhere between like half an arc minute to about 2 to 3 arc minutes, depending on your vision. So when you look at diffraction, it's actually an incredibly fascinating thing. Diffraction, what diffraction actually means is that it's a limitation put upon everyone, and no one can bypass diffraction, not the best lenses, not our eyes, nothing. And so no matter how hard we try, we can never undo the chains and handcuffs that are imposed on us by diffraction. I guess technically you can all blame Huygens for this, but it's all right. Now before we leave today, let me show you a YouTube video.
Here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? an interference pattern. We fired electrons, tiny bits of matter through. And we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
That's a preview of what you can expect in high-level physics. So, well, we'll see you all Friday.